Hi, I'm Lucas.
Hey guys, I'm Nadav.
I'm Jason.
I'm Rob.
I'm Zach, and we are Dark Matter Imaging.
So, firstly, we'd actually like to define dark matter imaging. NASA has a great definition, which I'm gonna read here. I quote: "Large galaxy clusters contain both dark matter and normal matter. The immense gravity of all this material actually warps the space around the cluster, and it causes light from objects located behind the cluster to be distorted and magnified. This phenomenon is what is called gravitational lensing. Now, this is an incredibly rare phenomenon. Several circumstances have to align perfectly in order for us to actually be able to see one, but it's a great probe for very profound quantities in the universe, including the distribution of dark matter, which is one of the most pressing research topics in modern physics. This is an example of a strong gravitational lens. This was an image taken by the Hubble telescope. This has been nicknamed the cosmic horseshoe. So this is the type of object that we're going to be looking for in our data. Our data actually consists of two primary sources. Firstly, we have Professor Xiaosheng Huang from the University of San Francisco, who built a residual neural network to detect candidates for strong lensing, and who actually produced 1,600 very likely candidates. We actually borrowed his data, which is in coordinate form, meaning that we don't have the images themselves, but we only have where those objects are located. We used those coordinates to query a public API and actually obtain the images for our own use. In addition to that, we have Brown's very own Professor Jan Del Antonio, who is a professor of astrophysics here, who has a different but deeper survey stored on the local supercomputing cluster nicknamed Oscar, which This survey actually has a 1 hour exposure versus Huang's 2 minute exposure. So that means that we're actually going to pick up a lot of dimmer objects, and we have a lot more galaxies and clusters and stars per unit area of the sky. And so these are actually in the form of what are called FITS files, as well as catalogs containing the coordinate of every object that his images have picked up. This is stars, clusters, galaxies, so on. So the data fields in these catalogs firstly, the two most important quantities are the right ascension and declination coordinates. This is basically just latitude and longitude. It helps us locate where the object itself is, and this is mainly what we're going to be joining on. And then we also have fields like the magnitude, which is per band of light how bright the object is. This is like red light, green light, so on. And we actually have from Huang's data the grade, which is how confident we are that something actually is a lens.
We started with 35.9 million data points from Del Antonio's data. That's 400 gigabytes worth of data. We filtered these to find only the most massive galaxy-like objects, as that's the only place where lenses can occur. We identified 4 million of these massive galaxy-like objects. And from there, we had our pool of lens candidates. We created this data visualization tool to showcase the scope of Del Antonio's survey versus Huang's. The black dots are the known lenses identified by Huang. The red dots are the galaxies we extracted from Del Antonio's data. We combine our data from both sources by their right ascension declination coordinates, then use various APIs to produce image cutouts of the thousands of objects in the survey. We will then use these FITS images to train our classification model.
Another step in data cleaning was to optimize our search. We hoped that discovering the properties of the known lenses could help us shorten the list of 4 million galaxy-like objects. Huang's known lenses had 3 light band data points, which we plotted and immediately noticed a particular pattern, because we assumed that the lenses we might find occur around similar objects. Then we set a 99% confidence interval for the light bands to shorten our list of galaxy-like objects to only look at those with similar band characteristics to those in Huang's dataset. So here are the intervals, and we filtered 4 million galaxy-like objects based on those and managed to reduce our list to only 368,000 candidates, which is a reduction of 91%.
And now for the model itself. So we borrowed our model from the Huang paper, which in turn borrowed a model from a paper by Lanous, The code was provided by Linus's paper in Lasagna and Theano, which we had to convert to TensorFlow and Keras because Theano is now deprecated, and this is sort of similar to PyTorch, which we talked about in class. This model specifically is a residual neural network, which is a special case of these CNNs, the convolutional neural networks that are used for image processing that we talked about a bit in class. These layers are special because they sort of jump forwards into different layers. So if you look on the left, you'll see that this is a single block of our model, which takes an input, which is then split into two sort of channels. The rightmost has a lot more processing that's going on, and then it's additively it's added at the very end, which sort of creates this jumping effect of a single input layer going into multiple future layers, and that's why we call this a residual neural network. And then if you look on the right, each one of those rectangular blocks is one entire block of an image on the left. So each of those contains probably 6 or 7 layers overall, which means that we have over 50 layers total in this model, and about 3 million or so trainable parameters. So it's a very large model. However, it's necessary because our input layer is a 64 by 64 by 3 layer array of image data. Huang used 101 by 101 images for their data along with the same 3 layers, but we found that the 64 by 64 sort of simplification offers a lot of time benefit in terms of training, and it seems to still get very good accuracy. And the output layer is a single neuron with a probability of being a lens, which is a continuous value between 0 and 1. And for the training data itself, we take our known lenses from the Huang paper and use the Legacy Survey API to get cutouts for those lenses, and for our non-lenses, we use a sample of the galaxy-like objects that we defined. And we do acknowledge that there's a possibility of an existing known lens in this set. However, by chance, other research has found that this is incredibly rare, about 1 in 10,000. So for the 20,000 or so that we choose for our training set, a pollution of about 2 won't really impact our training all that much. The data itself, being from 2 different sources, creates some challenges. One of them being a brightness difference, which requires some normalization. So the Legacy Survey is on a logarithmic scale, where our local is on a raw scale, so we had to convert that to a logarithmic scale, and then converted the brightness to values between 0 and 1 as to properly normalize and make sure that we are representing them equally, even though they're from 2 different surveys. Another challenge is that there's more noise in the local set because it's a deeper survey and there's probably more objects in the background, so we're kind of hoping in training that this won't impact our results that much and we'll still have a good result in the validation set. For a validation set, we chose to do 20% of the overall sample chosen randomly by TensorFlow every time the model runs. This helps us to not overfit on a static validation set as we're tweaking different data and model parameters. And so we have about 20 gigabytes of training data in cutouts, and this model is 3 million parameters, which creates kind of a compute power issue. However, the data is already on Oscar, which is the supercomputer that's used by the physics department for this research, so we chose to use the compute memory and GPU power of Oscar to train our data by writing some batch scripts to do just that. And so we run TensorFlow training on Oscar with GPU acceleration with like a crazy NVIDIA Titan V graphics card, which actually works pretty fast and efficiently. So here we see the results of our model training over 120 epochs with our 1654 known lenses and 20,000 non-lenses. We see that a clear increase in the test accuracy over time. And although the validation set doesn't quite match the accuracy of the train set, it still is very respectable, and the same with loss, indicating that our model is actually functioning in identifying lenses, gravitational lenses. And here we see a comparison between the train and test accuracies of our ResNet and some numerical baseline models that use other features such as the brightness in different bands. and we see clearly that our ResNet model beats out the other models, typically in train accuracy and certainly in validation accuracy, indicating that this neural network is indeed effective and vital to actually classifying known lenses in this way.
The intersection of Huang's dataset and our dataset actually yielded one object in common, and so we decided to use this object as a known true positive to gauge how well our model was doing. Most known negatives actually yielded around a 0% chance of being a lens, according to the model, whereas this true positive yielded a 40% chance. Here it is displayed for viewing. So we generally consider that to be a success. Now, moving on to the ethical concerns of our project, the data that D'Antonio uses is collected by the Cerro Tololo International Observatory, the CTIO, in the Andes in Chile. Now, this observatory is built in a region that was previously occupied by the Aymara people. And although they moved out prior to the construction of the observatory, there's still some concerns as to appropriating native land without consent. Beyond that, there's also some environmental concerns. There is a species of Chilean palm that is endangered, that is native to that region, and it's endangered because of overdevelopment. So perhaps the construction of this observatory did contribute to the endangerment of this species. So in general, we started thinking about how beyond the data itself, in fact, the instruments that we use to collect the data can have some ethical concerns. It can have some ethical implications as of themselves.